Hey everyone, welcome to the Chapter 2 lecture for Chem 100. This chapter is all about the structure of atoms and also radioactivity. So nuclear radioactivity actually has to do with atoms kind of crumbling apart from within. So it has to do with atomic structure. So again, here's the layout of the chapter, the different sections of the chapter, and the different topics we'll be covering. And hopefully by the end of this chapter, you'll get the joke. Do you have 11 protons? Because you are sodium fine. Okay, so atoms are made up of subatomic particles. So subatomic, if we broke up that word, sub means below, pertaining to the atom. So subatomic particles are the particles within the atom, or smaller than the atom. So an atom, a cartoon of an atom can be fairly well characterized by this picture here. All right, so in the center we have two different types of particles, of subatomic particles. We've got the neutrons, which are neutral. They have no charge. Where's my cursor? The neutrons have no charge, and the protons, which have a positive charge. And they are lumped together here. They form this tight center of the atom. And then floating around, or flying around really, in a cloud outside of the nucleus. They take up most of the space of the atom, except that they're very tiny. They take up the space by flying around, are the electrons. And the electrons here are negatively charged. So these are the three types of subatomic particles: protons, neutrons, and electrons. And you can even see here in this picture, the protons and neutrons are about the same size, and they are both larger than electrons, which are smaller. So you should know the three different types of subatomic particles, what their charges are, and where they are located in the atom. So the first rule to know about atoms is they are neutral by definition, meaning they don't have a charge. But they have positively charged particles and negatively charged particles. So in order for them to be neutral overall, it means that those positive and negative charges need to be equal and cancel out. So in other words, the number of protons, positive charge, must equal the number of electrons, negative charge, in an atom for it to be neutral. So that's sort of the first rule to know, is that atoms always have the same number of protons that they do electrons. Right? So we can figure out how many protons an atom has by using the periodic table. So the periodic table does have that kind of funny castle shape that we'll kind of discuss in the next chapter a little bit more why that is. But if you look across periods and you go in order, you'll see that there's numbers sort of on the top of each element symbol, and they go in order from 1 to 118. So that number on top is called the atomic number, and it represents the number of protons that are in an atom of that element. So every atom of helium on the planet has 2 protons. Any atom that has 2 protons is by definition helium. So that atomic number, also the number of protons, defines the identity of the element. Okay. So quick question for you. If helium has 2 protons, then how many electrons does it have? Ding, ding, ding! 2 is the correct answer. So little practice with your periodic table. Pull it out and look up these different elements, and provide the name for each of these elements with the following atomic number. So again, you're looking for the ones with the number on top. And I should have a periodic table handy with me. Bad chemistry teacher. So I can look up and tell you the answers. Ta-da! Okay. So number 8 is oxygen. I don't know if you can see it. Look at your own periodic table. All right, number 8 is oxygen. Number 19 on the periodic table is potassium, symbol K, and 50, if I scroll down, is tin, the symbol is SN, and 79 is gold, the symbol is AU. So there might be problems in the homework that ask you which element has the atomic number 46, and all you're doing is using your periodic table to determine that. Using your periodic table is never cheating, but it kind of is, because there's actually so much information you can glean from it. It is like a cheat sheet. So definitely have it handy always when you are participating in this class. Okay, so the mass number is sort of like the weight of an atom. And atoms are so incredibly tiny that we can't measure their mass in units of grams, or even something small like micrograms or nanograms or picograms are just not small enough. And so we have a special unit of mass that we use for measuring the mass of atoms, and it's called the atomic mass unit, the AMU. And by definition, protons and neutrons each weigh 1 atomic mass unit, and electrons weigh like 1/2000th of that. So electrons are so small that their mass is really negligible. And so we don't really count the mass of electrons in the mass of an atom. The mass of an atom is basically just determined by the number of protons and neutrons. So the mass number is the mass of an atom, and it's just the number of protons plus the number of neutrons. All right? So we can indicate all of this information about an atom using this nifty notation called symbolic notation, where we write the chemical symbol of the element from the periodic table, and then the mass number is a superscript on the top left, using my cursor there, and the atomic number, or number of protons, is written on the bottom right as a subscript, or sorry, on the left. Okay, so it's a little bit confusing because it's kind of flipped on how it is on the periodic table. The atomic number on the periodic table is usually on top, but in symbolic notation we put it on the bottom. Right? So we can look at this symbolic notation of an atom and we can determine how many protons, electrons, and neutrons are in a carbon atom. We know how many protons because all carbon atoms by definition have 6. The atomic number tells us the number of protons, so it has 6. And then we can figure out the number of electrons because we know protons and electrons have to be equal. So we said there are 6 protons, and since protons and electrons have to be equal, that means there's 6 electrons. And now to figure out neutrons, we just have to do a little subtraction. So we know that the mass number is the protons plus the neutrons. So the number of neutrons will be the mass number minus the number of protons. So we just turn this into a little subtraction problem, and that tells us that there are 6 neutrons. All right. So this is just a little cheat sheet for you, I guess, a slide for you to easily refer to while you're doing homework problems to figure out how many protons, neutrons, and electrons an atom has. These are the rules. The protons equal the atomic number, the electrons equal the number of protons, and the neutrons are not the atomic mass, the mass number, minus the number of protons. We'll talk about what atomic mass is in a minute. It's slightly different than the mass number. All right, so we have a sample problem here. How would you represent a fluorine atom that has a mass number of 19 in symbolic notation? So symbolic notation being this format here. So first we need the symbol of fluorine. We look at the periodic table and we find it on the periodic table, and it is just an F, not an FL, but just F is fluorine. It's near the top right of the periodic table. And above it on the periodic table is a number 9. 9 is the atomic number and the number of protons, so we put it down here. And the mass number it gives us in the problem, the mass number goes up here. So just getting some practice with writing these or reading them in symbolic notation, where each of these numbers goes, is good practice. Now it says determine the number of protons, electrons, and neutrons in this atom of fluorine. Well, the 9 there tells us that's how many protons there are. And protons always equal the number of electrons in an atom because they have to have a 0 charge overall. And then the number of neutrons, remember we just kind of turned this into a subtraction problem. 19 minus 9 is 10, so that's how many neutrons there are. Okay. So another practice problem for you guys to do. This is a good place to pause the video, or I might be pausing the video for you and having you fill it in yourself and then check your answer. All right, so I'm just going to fill it out pretty quickly. Hydrogen here, the number of protons. In fact, I'm going to do all the protons first. So this lower number is the atomic number. It tells us the number of protons. So this hydrogen has 1, aluminum has 13, sodium has 11, and lead has 82 protons. Number of electrons, since these are all neutral atoms, it's going to be the same as the protons. So I'm just copying the number from the first column into the first row into the second row. And for number of neutrons, we do that little subtraction problem. So 2 minus 1 is 1. 27 minus 13 is 14. 23 minus 11 is 12. And 207 minus 82 is 5, 2, 25. Okay? You'll notice that as atoms get bigger, they start having more and more neutrons. So smaller atoms oftentimes will have a similar number of neutrons as they do protons. 1 and 1, 13 and 14, 11 and 12. But as they get bigger, I just did this wrong, didn't I? 10 to 125. There we go. Not 25 neutrons, 125 neutrons. So that's quite a bit more than 82. And that's because, if you're wondering, all of the positive protons, those 82 protons, all stuck together in the nucleus, positive charges, like charges in physics, repel each other. So the nucleus is really uncomfortable with all of those protons jammed together so tightly. And so they need more neutrons. Think of the neutrons as sort of the buffers, the neutral things that help to protect the protons from repelling each other. So the more protons there are, the more neutrons there often are. So speaking of neutrons, while we said that all atoms of an element have the same number of protons, no exceptions, all atoms of carbon will always have 6 protons, all right? But they won't always have 6 neutrons. Some of them have 7 neutrons, some of them have 8 neutrons. So atoms can vary in the number of neutrons they have. And those different variants with the different number of neutrons will also have different atomic or different mass numbers, different masses. And so we call those different variants isotopes. An isotope is an atom of the same element that has a different mass because it has a different number of neutrons. So for carbon, for example, the one we looked at before was what we call carbon-12. It has a mass number of 12, and it has 6 neutrons. But carbon-13 also exists. It has 7 neutrons. And carbon-14 that has 8 neutrons. These are 3 different isotopes of carbon. They all have 6 protons, so they're all carbon atoms, and they also all have 6 electrons. It's the number of neutrons that differs, and since neutrons weigh 1 atomic mass unit each, it changes the mass of each of these. So when we look at the periodic table, the other number on the periodic table down here does represent mass, but you'll notice that it's not a whole number, it's a decimal. Whereas the mass number, when we do symbolic notation, is never a decimal. It's always an integer, a whole number, because it's just the number of protons and the number of neutrons added together. But what we see on the periodic table is actually an average, and we call this the atomic mass. So the atomic mass is actually an average. It's a weighted average of all of the isotopes of a given element. So you may be looking at this and thinking, well, 12.011 is not the average of 12 and 13 and 14. But again, it's a weighted average. So what that means, this is just my pointing out the difference between atomic mass and mass numbers. So that's an important thing to differentiate between. Mass numbers are whole numbers that are part of symbolic notation, but atomic mass is an average, and that's where it ends, the one you find on the periodic table. So a weighted average takes into account the quantity of each of those isotopes. So in reality, although there's 3 different isotopes of carbon, they exist in very different abundance. And carbon-12 is by far the most abundant of these different isotopes, with a little bit of carbon-13 and a sprinkling of carbon-14. And so when we average these and do a weighted average, the weighted average comes out very close to 12, because 12 is the most abundant of the isotopes. So 12.011 is what you see on the periodic table. We will not be doing the math to calculate atomic masses, but what I will have you do some problems in is in sort of estimation, I should say. So let's do this practice problem. Copper has 2 naturally occurring isotopes, copper-63 and copper-65. These, by the way, are mass numbers. Oops. The 63 and the 65, when we name an element like that, those numbers represent the mass number. I'm just going to put M hashtag for number symbol. Okay, that is the mass number. So there's copper atoms with a mass number of 63 and copper atoms with a mass number of 65. Based on the atomic mass from the periodic table, which do you think is more prevalent in nature? So it's saying that there's an isotope that has a mass number of 63 and an isotope that has a mass number of 65. If we look at the periodic table and we find copper, which is Cu, it has a mass of an atomic mass of 63.546. 63.546. So then we have to ask ourselves, basically, is that number, is that average, closer to 63 or 65? It's closer to 63, which means that there's more copper 63 on the planet than there is copper 65. So that when we do a weighted average, that average comes out closer to 63. So for any given element, I could give you different isotopes and then say, which one do you think is the most abundant or more prevalent in nature based on its atomic mass? And it would be whichever isotope is closest to that atomic mass. All right, so now that we know the basic structure of atoms, we can talk a little bit about radioactivity. So radioactivity has everything to do with the subatomic particles in the nucleus, the protons and the neutrons. So what radioactivity is it's a type of energy that's given off by the nucleus of an atom when it undergoes some rearrangement, when the protons and neutrons kind of shift around. It releases these energy waves. Sometimes it releases a particle, and that's what radiation is, what nuclear radiation is. So elements that spontaneously do this and just kind of always emit radiation we call them radioactive elements. And basically all atoms, all isotopes of all atoms, number 84 on the periodic table, which is polonium. All right, so starting with polonium, basically everything larger than that is naturally radioactive. And again, that's because they have very unstable nuclei, because they have so much positive charge packed together that those positive charges can't stand each other and eventually kick one of the other particles out. For the smaller atoms, for everything else on the periodic table, which is quite a bit, the periodic table, that's 1 through 83, some of the isotopes are radioactive and some are not. And we call those radioisotopes. So if it's, for example, gallium-69 is a non-radioactive isotope of gallium, but gallium-67 is radioactive. So gallium is not universally radioactive. There are some non-radioactive and radioactive isotopes of that element. So this process of the atom nucleus rearranging and emitting these rays of energy is called radioactive decay. And once the nucleus has rearranged itself and emitted the radiation, it is no longer radioactive. And it becomes really a new substance. So there's a few types of different types of nuclear radiation. We're going to focus on 3 of them, so I'm not going to talk about positron emissions. We'll cancel that out there. All right, so the 3 types that you should know are alpha radiation, or alpha particles. This is the Greek letter alpha that represents an alpha particle. An alpha particle is actually made up of 2 protons and 2 neutrons, which is basically the same thing as a helium nucleus. So this is the symbol that we use in equations when we're talking about an alpha particle and alpha radiation. Beta radiation is the second kind, and that's the Greek letter beta for you there. It's like a fancy cursive B. And what happens in beta radiation is a little complicated, and I'll explain it on another slide. But this is the symbol that we use for beta radiation. And then gamma radiation is indicated by the Greek letter gamma, and there's actually no particles associated with it. All 3 of these different types of radiation are what we call ionizing radiation. They form the energy basically of the particles or of the emissions can damage things like DNA or cell membranes, and that can lead to disease. And so radiation is something you want to minimize your exposure to, because it can mutate, cause DNA breaks and mutations that ultimately lead to things like cancer, which is why when you get like, well, an X-ray is a type of radiation, but it's not a type of nuclear radiation. It's a different type of energy. But if you work around radiation, like in nuclear medicine, you often have to wear detectors to measure the amount of radioactivity you're being exposed to. You wear a lot of protective equipment to protect yourself from being exposed to radiation, because again, it can lead to disease. So alpha radiation Alpha particles are actually the largest type of radioactive particles, and that means that they're actually the easiest to stop. And so alpha radiation can't penetrate past like the outer surface of your skin. Holding up a piece of paper would block alpha particles. They can be really damaging though if you ingest them, because they can cause damage to the gastrointestinal lining. They can get absorbed into your tissues and cause damage that way. But being exposed to them outside your body is not all that dangerous. Beta radiation can penetrate through a couple of layers of tissue. So it can't penetrate through the whole body that thick, but it can penetrate through several layers of tissue. We'll see beta radiations used a lot in cancer therapy, because you can embed it in like a tumor, and it'll be able to penetrate throughout that tumor, that local tumor, without spreading too much to the rest of the body. Gamma radiation is the most penetrating. It goes all the way through. It can even go through bone. So the X-ray I just have on here for reference, a reference point, X-rays are fairly penetrating. They can penetrate soft tissue but not hard tissue, which is why they're really useful in imaging bones, because the bones end up as a negative on the film, the part that's not exposed. So you get a nice clear silhouette picture of bones using X-rays, but gamma rays, not so much. They would penetrate all the way straight through. But you'll see we do have medical uses for gamma radioactivity as well. So when an atom undergoes nuclear decay, it is actually spitting out a particle for alpha and beta decay, and we can write that out as an equation, a type of chemical equation. So we call it a nuclear decay equation. So in alpha decay, the nucleus actually spits out 2 protons and 2 neutrons. And that is basically a helium nucleus. So we indicate that particle as symbolic notation for helium. And we can write this equation here. So we've got uranium-238. So uranium's, the mass number is 238 and the number of protons is 92. Right? Then it undergoes alpha decay. That's what the reaction arrow is. And it spits out an alpha particle. Well, what's left is no longer uranium because it has lost 2 protons. And remember, so now it only has 90 protons. And an atom with 90 protons is no longer uranium. It is now thorium. If you look at the periodic table, the element that has 90 protons is thorium. So what we have left now is a thorium atom that has also lost 4 atomic mass units. So now its mass is not 238, but 238 minus 4, which is 234. So when this uranium undergoes decay to become thorium, the thorium may or may not be radioactive in and of itself, but it's certainly not radioactive uranium anymore. It has decayed into something else. In beta decay, what happens is a neutron ends up turning itself into a proton, and an electron gets emitted from the atom. And so the beta particle is represented like this. So the E is for electron. Remember, electrons don't have any mass, so the mass number associated with this particle is 0. And we are losing a neutron and gaining a proton. So it's a little bit weird because it's saying we're losing -1 protons. In other words, it's like a double negative. So in other words, that's how we indicate that we actually gained a proton. So in this reaction here, we had thorium. Actually, this is the thorium from the problem before. And thorium-234 happens to be radioactive and undergoes beta decay. So it spits out this beta particle, and what we have now is one more proton. So we had 90 protons, but now we have 91 protons. We look at the periodic table and find out that that's Pa, which is Pa is protactinium. So it has turned into protactinium. The mass number, you notice, hasn't changed because there is no mass lost. So these equations are balanced if you look at the numbers. 234 plus 0 is 234. So the mass on the left side equals the mass on the right side. And 91 minus 1, equals 90. So again, the mass is equal on both sides of the equation. And if we go back to the alpha decay, we can see the same thing, that the mass number 234 plus 4 equals 238. Good, those are balanced. And 90 plus 2 equals 92. So this is a form of balanced equations here. So let's do some practice ones. So let's look at this first reaction. Well, the first question is, what type of decay is this? And what we're looking for is either an alpha or beta particle, to be able to identify that alpha or beta particle. And this is the radioactive particle that's emitted here, and this is indicative of alpha decay. Whereas this problem down here, this particle is indicative of beta decay. So we can go ahead and write those in there. I'm using the Greek symbols for alpha and beta. But now we need to figure out what this radioactive, what the product is, the daughter nucleus, if you will. So what we're saying in this first problem is that radium, Ra is radium, radium-88, it's losing 2 protons, okay? And so the new number over here is going to be 86. Or another way to think of it is 86 plus 2 equals 88. So that's our new atomic number. Well, 86 protons is not a radium atom. If we look at the periodic table, 86 is radon, which is Rn. The chemical symbol for it is Rn. And now we need to write the mass number for this product. All right, blank plus 4 equals 224. So that mass number is going to be 220. All right, so that would be the correct daughter nucleus or product of this radioactive decay. In the second one, we have manganese, radioactive manganese. All right, so the first thing we want to do is figure out this new number of protons. Blank minus 1 equals 25. So our new number here has got to be 26, because 26 minus 1 equals 25. Now we look up at the periodic table to see, well, what element is element number 26? And it turns out that is iron. And iron's chemical symbol is Fe. And then lastly, we need to write in the new mass number. Blank plus 0 equals 56 is just 56. There's actually no mass lost in beta decay, so the mass number stays the same. Okay, so that's some practice for you with some alpha and beta decay problems. Notice I did not run you through any gamma decay problems. You don't need to know how to balance those because gamma is not a particle. I'm sort of skipping over it. All right, so some practice problems here. Good to pause and try them yourself. Cobalt-60 is used in cancer therapy. Provide the nuclear decay equation for the beta decay of cobalt-60. All right, so the first thing we need is the symbol for cobalt, and we look on the periodic table and find that that's CO. All right, 60 is the mass number. The mass number goes on the top left. And on the periodic table, cobalt we find it on the periodic table, it's number 27. That's the atomic number, which goes down there. So the first thing we do is we write out the symbol for the radioisotope that we're given. And then it undergoes decay. So we draw our reaction arrow. And this question is asking about beta decay. So the first thing I'm going to write is a beta particle. And the symbol for a beta particle looks like this. It doesn't matter that in the previous problems it had the daughter nucleus and then the radioactive particle. It doesn't matter what order you write things in the chemical equation, as long as, like, you know, the products can be written in any order. There's no correct order. All right, the daughter nucleus, now we need to figure out. So we need to figure out what the new atomic number is going to be. So it's something minus 1 equals 27. So that would be 28. Now we look at the periodic table. What is element with 28 protons? According to the periodic table, it is nickel. And the mass number doesn't change because no mass is actually lost. 60 plus 0 is 60. All right, so that would be the nuclear decay equation for this radioisotope. And we can try one more, californium. Californium on the periodic tables, all the way down at the bottom, it's element number 98, and its symbol is CF. It was actually discovered at the University of Berkeley. I want to say it was at University of California, Berkeley. And the scientists who discovered it were trying to get some, like, positive sway with the college, so they named it californium. There's also a berkelium. Both of those elements were discovered at Berkeley, so that's where it got its name from. It is actually named after the state of California. Okay, so there's californium. It's undergoing, in this case it says alpha decay. So I'm going to draw an alpha particle, which is a helium nucleus. It's got a mass number of 4, 2 protons, 2 neutrons. And now I'm going to write the daughter nucleus. So blank plus 2 is 98. So the new mass number is 96, because 96 plus 2 is 98. And 96 on the periodic table is curium, named after Marie Curie. And the symbol is Cm, because Cu is already taken by copper. And the new mass number is going to be 247, because 247 plus 4 equals 251. So there's a couple of practice problems for you. Oh, I forgot I had animated this periodic table in so we could find these things. Well, anyway, here's californium for you. And it turns into curium. So, oh, so much for those animations. Alrighty. So, like we said, when an atom undergoes nuclear decay, it decays and then it's no longer radioactive anymore, or it's a new type of radioactive element. And so all elements that undergo radioactive decay, they do this at like a very consistent rate. Some will decay very quickly. They're very unstable. And other radioisotopes are more stable and they decay very slowly. And so we measure, or we indicate, the rate or how fast a radioisotope decays by its half-life. And we can measure the amount of radiation it's producing, and we call that the radioactivity. And the radioactivity units, there's several actually different radioactivity units, but the ones that are the SI units are the Curies, named after Marie Curie. First female to win two Nobel Prizes. and the first female to win a Nobel Prize in each category, I think. So 1 curie, a unit of 1 curie, is actually like a really high, dangerously high amount of radiation. So in like a nuclear med lab, we're talking about dosages of radioisotopes to give to people. It's usually like microcuries. So the half-life is the amount of time, it's defined as the amount of time that it takes for half of the radioisotope to decay. So for it to go down 50%. So if on day 0, you got a fresh sample of some radioisotope, so you have 100% of it is radioactive, all right? In this case, the half-life is 14 days. And so at 14 days, you now have half of that material is radioactive, so only 50% left. And then another 14 days later, after another half-life, you half it again. So now it's at 25% activity. And so on and so forth. So we go another half-life, we divide by 2 again. So after 3 half-lives, we have only 12% or 12.5%, I should say, activity left. So the best way to do these problems when you have half-life problems is to map it out just like this. So along the bottom, I will often write out each half-life time, and then the top, write out how much is left. So on the top here, what we're doing is we're dividing by 2 each space. Each time we go, we're dividing by 2. And what we're doing on the bottom here is adding 1 half-life. In this case, it's 14 days, so we're adding 14 days. I'll say add a half-life. I'm going to say add a half-life because I'm too lazy to write the E. Right? So like I said, some radioisotopes have very long half-lives. In other words, they decay very slowly. Right? And some of the poster children of that category, carbon-14, is the radioisotope that's used in carbon dating in archaeology. So it has a half-life of 5,730 years. It takes a very long time to decay. So you find a bone or something that's 20,000 years old, you can measure that, you can measure the amount of carbon-14 isotope that's present and do the math to figure out roughly how old it is, because there's still some carbon-14 left. Radioisotopes that are used in medicine, though, are going to be ones that have a shorter half-life, because we don't want to be giving people radioisotopes and have them be walking around radioactive for the rest of their lives. Maybe it sounds cool, like X-Men kind of stuff, but it's actually, of course, very damaging and can lead to things like cancer. So in medicine, we choose radioisotopes that have very short half-lives, preferably only, hours, but at the most several days. Iron-59, I don't even know what it's used for, but it's probably not a very popular one because it does have a very long half-life of 46 days, meaning that it takes 46 days for your radiation levels to drop by half. So let's do a couple of half-life problems. So again, I like to map these out. So we have radioactive iodine, iodine 131, and it has a half-life of 8 days. So if you have a dose of 200 microcuries given to a patient, how much activity is left after 32 days? So I'm going to start with at day 0, the day we give the patient the dose. We gave them 200 microcuries, okay? And then I'm going to say after 1 half-life, so in this case the half-life is 8 days, so we add that 8 days, so add 8, and now we're at 8 days, and at 8 days we have half as much left because it's been 1 half-life. So now we have 100 microcuries. but it wants to know how much is left after 32 days. So we kind of have to just keep going. So next we add 8 again to get, now we're at day 16, and we divide by 2 again. So now we have 50 microcuries left. And we go again, another half-life, another 8 days brings us to 24 days, and another reduction by half brings us to 25 microcuries. And then one more half-life, another 8 days brings us to 32 days. So as I go across the bottom row, I'm just adding 8 until I get to the 32 days. And in the top row, I'm dividing by 2 each time. I'm halving the amount by each time. So it's really good to go through this mapping process, because what a lot of people will do is they'll say, oh, 8 goes into 32 4 times, so that's 4 half-lives, which is true, and then they'll just want to divide 200 by 4. 200 divided by 4 is 50. That's not the right answer. So mapping it out is really what you need to do. The other tip that I have is this: make sure that you start at 0 days. The biggest mistake I see here, students understanding how to do the mapping, but they start out at 8 days. All right, that's after 1 half-life. So the starting time is always 0 days. One more practice problem. Iron 59 has a half-life of 46 days. So if we have 96 grams of iron 59 that was received in the lab today, like I'm a lab tech and it came in, how many grams will still be radioactive after 138 days? So radioisotopes don't have a great shelf life. You really have to get them fresh to use in patients, or be able to keep track of how much radioactivity they have left, because that will affect the dose that you give them. So again, we're going to map this out the same, except in this case we were given a mass of the radioisotope and not the radioactivity of it. So again, we start with day 0 and the full dosage, or the full amount, full mass. All right, after 1 half-life, and in this case the half-life is 46 days, so we're adding 46 every time we move across the bottom row. So at 46 days, we're going to have half of that 96 grams left that are radioactive. Half of 96 is 48. So we go another half-life because we're trying to get to 138 days. So add 46 again, we're at 92 days now. And there's half of 48 left, 24. And then we add 46 again, now we're at 138 days. Half of 24 is 12, so 12 grams of that material, of that 96 grams, is still radioactive. So radioisotopes, radioactivity is important to understand if you're going into healthcare field, because radioisotopes are used a lot in medicine. And there's 2 main ways that we use radioisotopes in medicine. And the first is in diagnosis. We use it in a lot of medical imaging. So radioisotopes that are used in imaging are called tracers, because they literally will trace internal organs, and you can take a picture of them. So they are often either injected in your veins or they're ingested in like a pill. And then they, depending on the isotope that you're given, certain isotopes will tend to localize to certain tissues. So for example, iodine 123, iodine localizes in the body to the thyroid, which is like a butterfly-shaped gland in your neck. And so these areas where there's a lot of black, that's where the iodine is. That's from the radioactive iodine that leaves an image on a screen. We call these hot spots. We say that radiation is hot. And so this would be a healthy, normally functioning thyroid. But in the picture on the right here, this thyroid, this lobe of the thyroid has a big cold spot. In other words, an area where where the radiation is lacking, which means that that isotope is not localizing or getting taken up by that part of the thyroid because it's not functioning properly. And so that is a use of radioisotopes for imaging. Another one is fluorine-18, which can localize to really metabolically active areas of the brain and can be used in PET scans, positron emission technology. So this is a cool way to see the brain in action, like live action. So this is a healthy brain, and you can see lots of hot areas. The red and yellow areas are very active, whereas in an Alzheimer's brain, a lot of those areas have become cold spots, blue or black. They're not as active. So for diagnosis, we want to choose isotopes that are gamma emitters because you're injecting them or ingesting them into the body, and then you stand in front of like a screen or a detector that can detect that radiation. But it only detects the radiation that actually leaves your body and comes out and hits that detector. And remember, gamma radiation is very penetrating, so it can penetrate all the way out of your body to that detector. So you definitely want to use gamma emitters for imaging to make sure that it can penetrate through the body. And you want to use as low dose as possible because gamma radiation is damaging, and you want to do as little damage to the person as possible if you're just trying to get an image of something. Another use of radioisotopes in medicine is actually on purpose to damage you. And we can use it as therapy, particularly for cancer, for treating tumors. And so in this case, we want to use a higher dose because we actually want to cause harm and cause ionizing radiation to the cells. But we don't want to use a gamma emitter because we don't want it to penetrate the whole body and damage everything, and we don't want it to leave our body and penetrate the person in bed next to us at night. So we want to contain that radioactivity a little bit more. So usually when you're getting like radiation therapy, they're using a beta emitter if it's something that's like injected. Some types of radiation therapy will use gamma emitters, but they'll they'll lay you on like a bed and they shoot the gamma rays at you, like with a laser. So the gamma radiation is not actually, the radioactive material is not being put inside you. So when you leave, you're not radioactive. But beta emitters can be given, ingested or injected, and stay in your body and localize to a tumor and selectively kill the tumor. So a good example of this is with iodine. So iodine has multiple radioisotopes and multiple non-radioactive isotopes. So iodine 123 is the one we saw in this slide here that's used for imaging the thyroid. But if you have thyroid cancer, they can treat it with a different isotope of iodine, iodine 131, which is a beta emitter that you can ingest, and it'll localize to the thyroid and actually kill thyroid tumors. Oh my God, my cat just walked in and she scared me. Hi, everybody. So yeah, with the 123, for imaging, you definitely want to use small doses because when the person leaves the diagnostic imaging lab, they're still going to be emitting some of that radioactivity, and you don't want them walking around damaging everybody in their presence or damaging their own thyroid. But for somebody who's getting cancer therapy, radiation therapy, then you do want to give them larger doses, but you want to make sure that the radiation sort of stays in their body and doesn't exit the body. So you want to use a less penetrating type of radiation, which is beta radiation. All right, so that is the end of chapter 2, all about the structure of atoms and how atomic nuclei can decay and emit different types of radiation, and then of course how that radiation can be damaging, but also how it can be useful to us in medicine. The end.